Zero Knowledge session. And our first talk is titled Skyscraper, Fast Hashing on Big Primes, and will be given by Fabian Schmidt.
Hi. All right, thanks for the introduction. So my name is Fabian Schmidt. I'm from TU Graz, Austria, and I'm going to present the zero-knowledge proof-friendly hash function Skyscraper. This is a joint work with Clémence, Lorenzo, Dmitry, Katarina, Christian, Markus, and me. So what are we going to talk about? We're going to talk about hash functions, but hash functions for a specific purpose. So we will look at proving some relations. We usually need to transform whatever relation we want to prove into some arithmetic representation. And this means in particular for hash functions that we need to have a good algebraic representation of our construction. So the cost is really dominated by the cost of proving such a hash function pre-image, for example, is really dominated by the algebraic representation that we can have. And traditional hash functions, if we look at SHA-2 or SHA-3, for example, have really bad algebraic representations, which is obvious because this was not considered at the time of designing these hash functions. So there's a big push now towards tailoring the design of hash functions towards efficient provability in the various proof systems. So we focus on large primes. For those who are familiar with proof systems, they know that there's many different flavors out there. So there's proof system working on binary extension fields, so binary polynomials. There's proof system working on small primes, and there's proof systems working on big primes. So there's a pretty big field, and in this paper we really specifically focus on large prime fields, which are used in pairing-based cryptography, and thus are super friendly for snarks and allow for fast verification times and give small proofs. They are thus also efficiently used on-chain. All right, so what do we want to do? We want to improve performance for the large prime fields. The first step we take here is to use a Feistel structure instead of an SPN. Here, as an example, we have, how is this? Yeah, on the right side, we see the classic SPN structure, which is a substitution permutation network where we interleave nonlinear layers and then affine transformations, which are usually a matrix multiplication with a constant addition. And on the left side is a Feistel structure, and this structure has the particular property that if we want to design a permutation, on the right-hand side, every building block has to be invertible, meaning that if we use, for example, a power map here, then also this power map has to be invertible over the prime field we're working on. While in the Feistel structure, we can use non-invertible building blocks. And it turns out that these non-invertible building blocks, even though the Feistel has some disadvantages, the non-invertible building blocks allow us to create even faster designs. All right. We also wanted to make the design as simple as possible to minimize attack vectors in the design and cryptanalysis, but also to make adoption in both the plain implementation and the proof system implementation as simple as possible. In total, our scheme only consists of two different building blocks, which are non-invertible squarings and non-invertible S-boxes, or bar layers as we call them, and I will go a bit into detail. And the actual hash function is then just a consecutive execution of these building blocks. So what we also want to do is we want to really optimize out all the individual building blocks that we have, which is only two building blocks. And the first one is the squaring operation, where we really tailor the squaring operations towards the Montgomery reduction. I guess in this audience, most of you will be familiar with the Montgomery reduction. It's essentially a way to more efficiently reduce numbers after multiplication in a given prime field. And it has, however, a peculiarity, which is that at the end of the reduction, we get an additional factor, which is just a constant multiplied to our result. So in a use case where we want to use Montgomery reduction, we have to account for this additional constant, which is multiplied to the result, to either peel it off afterwards or already multiply the inputs such that the result matches what we want to have. However, since we're designing a hash function and such a constant shift in the parameter space does not matter to us, we can really improve the performance by already integrating this parameter into our definition of the square operation, which then retains the nice statistical properties. However, it is much more efficient in software implementations. All right, and also for the problem, of course, if we only use algebraic building blocks to build our hash function, then we're really prone to algebraic attacks if we don't manage to really increase the degree of the algebraic degree of our construction. So what we use in Skyscraper are building blocks called lookup tables, which are available now in zero-knowledge proof systems. And with these building blocks and a circular rotation, we build an S-box or a nonlinear function that really boosts our algebraic degree with relatively cheap cost in bit operations and also in proof system implementations. All right, so now we have covered all the goals and motivations. So how does the construction actually look like? So the original proposed construction looks exactly like this. So we have consecutively 2 squares, 2 bars for a total of 10 rounds and 2 squarings in the end. And for the square, as I already said, we have a non-invertible power map because in the primes we consider the squaring operation is non-invertible. So not all elements of the prime field are actually in the range of our function here. What we additionally do is we speed up the squaring with the Montgomery reduction, which means that we define the function already to include this division by the sigma factor. What this means in essence is that you can use a Montgomery implementation without transforming your shares into this representation first. So you really save this step of transforming into it. And why is it relevant? Because of course in the bars operation where we directly operate on the bits, we would have to otherwise switch out of the Montgomery representation after this evaluation and before this evaluation and switch back into it afterwards. So to really save this switching back and forth, we already include the Montgomery constant here. So the squaring operation from a cryptographic point of view gives us very good statistical properties. So it protects us against a wide class of statistical attacks. And the bars operation, as I already said, is there to really boost the algebraic degree, which is a protection mechanism against a wide class of algebraic attacks in the cryptanalysis. And yeah, as I said, it's really sped up by bit operations. So while this is a nonlinear function that's evaluated with a lookup table in the zero-knowledge proof system, in the plain implementation, there is an efficient bit representation of the algorithm here, which means that in essence, we don't have a problematic side channel or something like that. All right, so one thing is that we can see here that we have 2 input values, XL and XR, which means these are really our 254-bit prime field elements. But what about larger state sizes? So in a lot of settings, maybe for Merkle tree, where you want to hash more than just 500 bits at a time, it might be required that your hash function actually handles larger inputs without putting it in a more complex mode of operation. And of course, for the Feistel construction, without going too much into detail, there are ways to extend the Feistel construction to handle more values. However, if we would extend this to maybe 4 or 6 branches, then this would also need to have careful evaluation because some properties might change and the cryptanalysis would not be as clean. So what was our solution to the white state dilemma? Was in essence, instead of using the prime field as we did, we used the prime extension field. So this means that every value in both the XL and XR are now actually polynomials of the prime extension field, where our reducible polynomial g of x has degree n, which is settable, however large you want your state size to be. And of course, this polynomial g has to be irreducible in the prime field Fp. And yeah, in essence, what this means as a consequence is that you evaluate your square really over the polynomial values and then reduce by the irreducible polynomial. And for the Bars layer, or like the nonlinear layer B, you interpret your polynomial that you have just as a vector of elements, and then you extend the bar functionality to this vector instead of single elements. All right, and if we look at the performance, this performance impact this has, we really see, okay, for the Bars layer, we have a somewhat linear increase, meaning that this representation as a vector and direct application really does scale as expected. For the square, as we can imagine, the polynomial multiplication really has a much worse impact. And in fact, it shows that for our initial experiments, extension field degree 3 was the only one that could be argued. Beyond that, it's just much more inefficient. And in real practical implementations, probably you would stick to degree 1 or degree 2 extension field. All right, so how does the bar component look like? If we now use a toy example where we have a prime which is only 15-bit large, then in this prime field, given some value here, our bars layer would essentially split the value into the 8-bit components and then do a circular shift by half of the size and then evaluate the S-box on the individual components. So why do we do that? As I said, the S-box already is a bit-based function, so it has no nice algebraic representation. However, since it's a lookup table, we can still evaluate it in our proof system. Given that it doesn't have a nice algebraic representation, boosts the algebraic degree of the underlying representation in an algebraic model, and also using this rotation here further increases the algebraic degree a lot. All right, so how does it look now if we extend this to larger extension fields? If we have a polynomial now, which is essentially just two values, we can interpret them also as a vector of values and then do decomposition just as we would with a single value essentially, and then the rotation still is the half of the length of a single value. So in essence, in this toy example, it's only a single byte that is shifted. All right, and we can extend this also, of course, to 3 dimensions, and I guess you catch the drift how this would go on, essentially. All right, so if we look at now the proof system performance, if you're familiar with the topic, then of course you know that this is a kind of hard comparison to make. It's always a bit of apples versus pears, because in essence, you have so many different proof systems all optimized for different metrics. But what we did is essentially to compute the area degree product. This is a metric introduced, I think, already in the Poseidon paper, at least also in the reinforced concrete paper, where you essentially use the witness matrix, essentially all the intermediate values that you have in your algebraic representation that you use to generate your proof. And this witness matrix has a specific size. And of course, the cost of proving is determined by the size. But what's also a large factor for determining the price of such a proof is the maximum degree that you have in your computation. So we kind of have this metric where we try to combine the size of the witness matrix with the maximum degree that we have. And given this metric, we see that we are somewhat more expensive than maybe Rescue Prime or Poseidon. It also, of course, depends, because our construction is required to support lookup arguments, which is also a restriction, of course. But we see that for large primes, our native performance is just much better at this point. All right, so unfortunately, there's been a bit of a security update, because in the meantime, since the release of this paper, there has been a small paper by Antoine Bach, who essentially was able to make a rebound attack on our work, and he found a distinguisher on the 9-round version of our construction, which meant that at the time, this removed all of our security margin. So what we did in the meantime already is we updated our ePrint and released Skyscraper version 2 in close contact also with the attacker. And we are now quite confident that the addition of 4 square layers at the beginning and at the end does indeed fix the problem. So why do we only increase the number of squares and not bars? I already said that the bar layer uses lookup table arguments. So in the proof system, the bars layer is really much, much more expensive than the squaring. And overall, the squaring has an acceptable impact in the plane performance. And additionally, the bars layer increases the algebraic degree, protecting against algebraic attacks, while the square layer gives us good statistical properties, which protects against statistical attacks. And since this attack nature was statistical, or since this attack was statistical in nature, and the algebraic security margin seems to hold quite well, we increased only the square layers. All right, so before we go into the plane performance, I want to quickly recall a mode of operation. In essence, when we design a hash function, very often what we do nowadays is to design a pseudo-random permutation. So you have a permutation, and then you put it into a mode of operation, kind of a way how to use this permutation to actually get a hash function out of it. So what we had here is, if we go back, this is our skyscraper permutation. We have 2 inputs and 2 outputs. However, if you think about the layers that you have, it will always be possible to take the 2 outputs and get back to the input. This is because it's a permutation. However, this is quite the opposite of what you want of a hash function. So if we use classical compression mode, then we just take our 2 inputs, put it into the permutation, add the first input to one of the outputs, and then just take this single output as the hash output. And you will see that already it's quite impossible to get back to the original values. And additionally, and maybe more known, is the sponge construction. The sponge construction, in essence, only adds a single message element per permutation. However, this is really defined to go on as long as you want. So you can have additional permutations for each block of inputs. So this is really tailored towards many inputs. And while you might think, okay, this is quite obviously having more messages per permutation call, for the sponge mode, there's quite good cryptanalysis giving good bounds on the security of this construction if the permutation is pseudo-random. So we really went from, okay, we need to have a hash function that has all these nice properties to just, okay, we just need a permutation that's random enough. And that's why in a lot of cases, sponge mode might be preferred. So what we did is now we compared the sponge mode and the compression mode for different hash functions for large prime fields. We have rescue prime, one of the first really optimized towards proof system performance. And I have to remind here that rescue prime really has superb proof system performance. However, as we see, the overhead in the plane domain is just maybe not acceptable for all use cases, especially if we are looking at use cases like building large Merkle trees where we really have to do a lot of evaluations. Then if we look at Poseidon, the de facto industry standard, I would say, for zero-knowledge friendly hash functions, then we see already, even with the Poseidon 2, the optimized version where you have a lower number or a set of smaller round constants, even there you still have quite a large overhead. And with our work, with the initial results, we really push down the number for compression, and also in the sponge mode, where our design is maybe not as optimal as others because we grow more than, for example, reinforced concrete, we still exhibit much larger performance. However, as I've said before, we now have an updated version, and this had the effect of really pushing the numbers, unfortunately, quite a bit. However, we still retain quite a big gap between the different compared to the other designs, essentially. And what we see here is that the bonus that we have of accepting a larger state size now almost vanished. So for the new version, unfortunately, the squaring scales much worse. So in essence, there will only be a few use cases where really this more complex extension field construction will be more efficient. All right, so in conclusion, we have a new hash function. It's now called Skyscraper version 2. It's efficient in plane. It has this Montgomery reduction optimization. It has an efficient bit representation for the nonlinear function. And it's also quite efficient for proof systems with large primes. It is in the plane performance somewhat in the same domain as SHA-3. And the Feisler strategy allows us to use these very efficient nonlinear building blocks. We can remove the affine layers, these matrix multiplications, which are very inefficient for large primes, and we have a simple design. So we use the same design for small state size and larger state size, and our generic bar construction does not need fixed primes. So any prime larger than 254 bits is valid for our construction. Thank you very much.
So we have time for questions. Is there any question? Okay, so I may ask one question. So you mentioned that there is a rebound attack for the first version, and then you develop the second version. So how about the other attacks? I mean, in the paper you have many proofs for the first version. Does this proof also apply to the second version? And is there other kind of attacks that you need to consider?
Yeah, thank you very much. I think that's a quite important question because, of course, we can do all the cryptanalysis we want, but at the end, the confidence is really built over time. And we did careful analysis of a lot of attack vectors. And we are now confident that we definitely fixed the attack vector of a rebound attack. But also, it needs more cryptanalysis, also from outsiders, having a different perspective on the construction to really gain more confidence here.
Any other question? So let me ask another one. So I'm doing verification. So I wonder if you have your implementation is in which language? Is in C or assembly or?
You mean for the proof system? Yeah. So our plain implementation is in Rust. It's essentially uses some finite field libraries, I think ArcFF. And for the proof system implementation, we use the Halo 2 proof system, where there's lookup tables supported, essentially.
Okay, so if there's no other question, let's thank the speaker again. So our second talk is SIMD MSM. SIMD Accelerated Multi-Scalar Multiplication Framework for ZK SNUGs. And the talk is given by Ray Zhang. And let's welcome the speaker.
Hello everyone, my name is Jiang Rui. It's my honor to be here to have this presentation. Our project is SMD MSM. It's a SMD Accelerated Multiscalar Multiplication Framework. So let's start. First, let me introduce the background. Nowadays, zero knowledge proof are booming. And the ZKP allows us to prove the statement's correctness without revealing any private information. And they are widely used in many areas, in blockchain such as Zcash, in privacy preserving, and many other applications. And in pairing-based ZK SNUGs, MSM is the core bottleneck. And we can say that MSM is a linear combination of elliptic curve points. Look at this formula, where Ki are scalars and Pi are elliptic curve points. And the MSM may account about 70 to 80% of ZK SNUG the whole proving time. Although there are many works about accelerating MSM in GPU or FPGA platforms, we think that for most users, they are more familiar with the personal computer. And we think accelerating MSM on CPU platforms can make CPs more user-friendly. So SMD is the main tool in the CPU platforms to accelerating. And single instruction multiple date is that, for example, instead of add A and B one at a time, we can add multiple pairs of them at just one operation. And the previous works has shown that SMD can accelerate elliptic curve operations, and they show significant performance improvement. So we said we can use SMD to accelerate MSM in large scale too. And then naturally raises up our key question of our research. Is it possible to use the built-in parallelism of modern CPUs to improve the efficiency of MSM computations? I will briefly introduce the parameter algorithm. Is a core foundation of our research. We divided into 4 stages. The first is task decomposition. We divided the whole MSM into several parts, into several subtasks according to the window size S. Next, for every subtask, it's a bucket accumulation. Is to set every point into every bucket according to the subscalar's value. For example, this is 0101 is equal to 5. So we'll put the point 8 to the bucket 5. And I'm sorry, this is a writing error. This is B5. So according to its value, we can put this point into this bucket. Next, we will aggregate all the buckets points value into a final result. Finally, we combine the results of subtasks and we get the final SMS result. Before the acceleration, we face some difficulties. The first is that it's hard to parallelize between subtasks by SMD. Because SMD requires the same operations on all data. But in the bucket accumulation stage, the pointer may be added into the bucket, or it may be simply copied into the bucket when the bucket is empty. So they are completely different operations. And the number of the subtasks often not a multiple of the parallelism degree. That make underutilization. So we will turn to use SMD to accelerate a single subtask. But parameter sequential dependencies will limit the parallelism. And within a subtask bucket accumulation stage may cause the writing conflict when two or more points may be added into the same bucket at the same time. This is a writing conflict. And we also think memory overhead is an important problem too. MSM itself may need GB level point storage on CPU. And we must minimize the extra memory from parallel architectures. Now with this question, we see next page. Before the acceleration, let me introduce some tools we will be using later. This is some arithmetic engines implemented by SMD. We divided the PI into 3 types. The first is PI star. PI star denotes that point addition when Z1 is equal to Z2 is equal to 1. And the PH plus denotes the mixed addition, point addition. And PI hash denotes that Z1 is not equal to Z2 is not equal to 1. And in the parameters bucket accumulation stage, it's mainly use mixed addition. The mixed addition is about 11 times multiplication. But if we use this tree-like structure, it only costs 9.5 multiplication. The tree-like structure is like this picture. We will first add the 2 points by pi star, and then we will add this point to the bucket by pi hash. And this can have a performance improvement. And this tree-like structure can be perfectly combined with the overall architecture later. And according to the PI type, we design 3 kinds of engines. We need to remember these 3 names. We will use them later. And we use AVX instructions to implement them on both group 1 and group 2. We instantiate 8-way PI. Here is the benchmark. We use the baseline is relic, and the easy mode is implemented by C language, and the ASM mode is implemented by assembly language. The speed up is about 2.7. And it should be noted that our framework is not limited to AVX. It can be applied to any other SMD instructions just by replacing the underlying elliptic curve points engines. Now let's start our first attempt. We have mentioned that in the first difficulties, we will not use SMD to accelerate multiple subtasks. So here, we use multi-threading to have a text level parallelism. And we use SMD to have a data level parallelism. The core of data level parallelism is that accelerating back to the accumulation stage by SMD engines. But how to use the SMD engines is still a question. Surely we can get a buffer for every bucket, but this method can use too much memory usage. For example, this is the 8-way buffer. It has 16 points, and in BLS curves, it will cause a large memory overhead. Also, if it falls, it will cause the SMD engines. But how to deal with this result is still a question. After getting chi is the parallelism degree. After getting the result points, it's still difficult to parallelize the PI to the bucket of these points. So we have the second attempt. We will open only one buffer, one global buffer of size double K. When the buffer is full, a K-way parallel PI is performed. But how to solve the writing conflict when 2 or more points are intended to be added to the same bucket in the same round of SMD PI operations? According to this, we come up our state control mechanism. Based on this, we have the third attempt. We will use multiple level buffers. On the one hand, different types of PI need different SMD engines. On the other hand, use the tree-like structure we mentioned before. We'll have a nice performance improvement. Now let's look at our final three-level SMD scheduling mechanism. The 3 level is the task level, loop level, and the date level. For the task level, every thread will deal with a sub-MSM, a subtask, and every thread will have a buffer 0. The buffer 0 consists of L is a bucket ID, and the bucket. And here is the address. This address is, for example, 0.50011. This is equal to 3. So we will put its address into here, And he will wait the next point to be added to the bucket 3. And when the next point is come, the point's address and this point's address will be put into the buffer 1. So here is the loop level. Here is the loop level because I'm sorry. Here is the loop level because MSM has a large scale. So we will split it by multiple children threads. And every thread will have a buffer 1. The buffer 1 is, I mentioned before, when the buffer 1 is full, it will trigger the data level. So here is the data level. When the count of the buffer 1 is equal to k, it means the buffer 1 is full. So we will trigger the SMD-PI define engines and put the result into the buffer T. The buffer T is consists of the IDI and the points. Then for this buffer T, we can't add it directly into the buckets because there may be some writing conflicts. So we need to organize the write-back order and put them into the buffer 2. When the buffer 2 is full, then trigger the SMD-PI project engine. Then the result can be written back directly into the bucket. So how we solve the writing conflict? We have a state control mechanism. Here is the 6th stage, and the first stage is state 0. It's an initial state, and now the buffer T is empty. The state 0 will go to state 1 or state 2. In the state 1, no same scalar in the buffer. It means that now there is no writing conflicts. So we can call SMD-PI project engine directly to write back the buckets. But for the state 2, there have some points has the same scalar. So there will be a writing conflict. We should wait until the next k points pushed into the buffer T. So go to the state 3 and the state 4. For example, we don't require logs or delays the conflict. We choose to solve the conflict. We will use pairwise add or write back. For example, there are 3 scalar 3, and the first we will add them in this round, and the next there is no conflict. We will compute to put it into the bucket. So this conflict is resolved. And the difference of state 3 and state 4 is that next, this state will have no conflicts, but in state 4 it still have conflicts. So state 9 will go to the finally go to the state 1, and state 4 will finally go to the state 2. According to this state control mechanism, we're solving the writing conflict. But there still have some work to do. In the finally, the buffer 1 and the T and the buffer 2 may be not empty. So to solve this, we can directly call the SMD engines. This will not cost many time. And if the buffer is not full, just a dummy run is okay. But for the buffer 0, they still have some points that waiting for the next point to be paired. But there's in the finally, there are no more points. So we use the SMD-PI mix engine. This engine we mentioned before that, but we have not used it. And this part is just a mix addition. We just need to add this point to the bucket. So we call the SMD PID mix engines to perform this mix addition in parallel and put the results back into the buckets. We use AVX instructions to implement our work, so we name it AVX MSM. And the LabSnark library is a famous library of ZK-SNARK. So we replace its MSM with our AVX MSM in both Group 1 and Group 2. We integrate AVX into Group 16, and we name it AVX ZK. We use JSNARK to better evaluate AVX ZK's performance in real-world applications. In the way to integrate the LabSnark, there are some problems, and we come up some tricks. For example, the first is duplicated points into the same bucket. When I implemented MSM and AVX ZK, I found that if 2 points are same in the SMD PID fan engines, when they are added, we will get a fault result. This is because that the current PID star formulas don't have a strongly unified arithmetic. So for this problem, we have 2 methods to solve it. The first is that to deduplicate it by hash map. We can merge the scalar with the same points by hash map k and p. It has a low cost, and we can reduce the MSM's scale too. And this part can be pre-checked once. At first, you can check that if this arithmetic circuit has deduplicated points appear. If you are sure that no deduplicated points appear, you can just skip it in the next time's implementation. The second method is that we can use Twisted-Edward form. Then this Twisted-Edward form in extended coordinates in Twisted-Edward curves, the PID is more efficient. For example, the mixed PID is just 7 times the multiplication. And the most important is that the PID formula is strongly unified. So this method can fundamentally avoiding the errors. And here is the evaluation, environment, and configuration. We use the BL as elliptic curve. And our work is available at the GitHub. Here is the evaluation of our AVX MSM. Our baseline is still the Relic library, and the speed up is about 22 to 27. Also, we compared our work with the work LFG, and its speed up is about 12 to 15. And it should be noted that the LFG uses the pre-computation. So when the scale is large, it will not support the MSM computation. And this is the evaluation in Group 1 and Group 2. The speed up is compared with Relic. The speed up is about 20 to 27. And compared with LFG, the speed up is 13 to 15. And this is the AVX ZK. The speed up is about 11 to 20. But for the large scale, the LabSnark will terminate automatically due to the excessive runtime. We also use the real-world test, but the actual scale of MSM computation and their proportion in the overall proof calculation are relatively small. So the speed up is smaller than this. The speed up is about 3 to 5. And my presentation is over. Thanks for your attention. Is there any questions?
Is there any question? Okay, let me ask one question. So can you talk about the future work of this research?
We can say that the parameter has this three stages, and we now mainly accelerate this stage, the bucket accumulation. But this stage is not easy to accelerate in the CPU platforms, especially. You can see that in this stage, we need to add the more step by step, so it is not easy to parallelize them. And our next step, our future work will accelerate this part. We will design a parallel method to accelerate this part.
Thank you. Any other question? So then I may ask another question. So you mentioned that your approach can be applied to other SMD architectures. So will this degrade the performance?
The performance is according to the engines we use. If the engine's speed up is larger, the final performance will be larger. But the overall architecture has no problem. It's just replace the engines is okay.
You mean that the performance of your engines will not be changed on other SMD architectures?
Other SMD engines is okay.
Okay. Thank you. Any other question? So if there is no other question, let's thank the speaker again.
Thank you very much.
Okay. So the next talk is titled OptiMSM, FPGA Hardware Accelerator for Zero-Knowledge MSM. And this talk will be given by Zenter Potier and Thomas de Ruyter.
Thank you for the introduction. My name is Thomas, this is Xander, and together we will be presenting Optimism for you. This is a joint work with Jonas, Wouter, Michiel, and Ingrid. And Optimism is an FPGA hardware accelerator for the multiscalar multiplication, or MSM for short. We already saw some motivation in the previous talk, but let's give you a quick recap. Why do we accelerate a multiscalar multiplication? Well, this is because it's the dominant bottleneck in ZK snarks, taking over 70% of proof generation times in those proof generations. What is the definition of an MSM? Well, given a list of elliptic curve points pi and a list of scalars ki, to take the inner product between the two lists and then add all of these results together. We're working over elliptic curves, so the basic operation is the elliptic curve point addition, which in turn is made up of many modular multiplications. So this means that we will have plenty of work to do on our FPGA before we need new points, so we will be computation bound. This means that if we can reduce the number of elliptic curve point additions to compute one MSM, this will directly reduce the latency, the computation time of an MSM. This will be the first half of our presentation, and afterwards, Xander will talk to you about the efficient hardware implementation that we made for it. So, we also use the Pippenger's algorithm, so let's give you some intuition of how this algorithm will actually reduce the number of elliptic curve point additions to compute one MSM. We have to multiply every point of elliptic curve point pi times a scalar and then add all of them together, but Pippinger told us that instead of doing that, we will first accumulate all of the points that have to be multiplied with the same scalar together in so-called buckets, that's just storage elements, and only then compute this 1 times bucket 1 plus 2 times bucket 2, and so on. And what we save here is that instead of multiplying every point with a scalar, we will first accumulate them, and then only the number of buckets that we have to multiply by these scalars. This was a toy example with scalars going up to the value 3. In a realistic case, these scalars are way larger, they're b bits long, so we will have to split them up into separate subscalars before we will be applying this Pippinger algorithm to it. And do the accumulation step for each of these subscalars, and only then go to the aggregation step afterwards. What we will do here is if we have a point pi, we will be adding it to a first set of buckets depending on the first subscalar, to a second set of buckets depending on the second subscalar, and so on. And the important trade-off parameter here is the window size that we call C, because if you increase C, you will have fewer windows, and therefore you will see that the accumulation step becomes cheaper, but the aggregation step has to compute on 2 to the power C buckets, so this means that if we increase C, we will have an exponential increase in the operations that are left in the aggregation step. Moreover, you need to keep all of these intermediate results, so if you increase C, you will need more on-chip memory to keep all of those buckets to keep all of the intermediate results. The Pippinger algorithm was improved many times already in the literature. We will now give a short overview of 3 of those optimizations because we're combining them in our paper, but more details you can find in our paper because we will only give a short overview. The first optimization is a signed digit representation, and this exploits the property of elliptic curve points that the negative of an elliptic curve point is very cheap to compute by just inverting one of the 2 coordinates. So we can exploit this to limit the number of buckets that we need to keep for every window by half by taking all of the buckets values, all of the subscalars for the buckets that are larger than 2 to the power C, and write it down as, in this example, we can write down 39 as 64 minus 25. The 64 is a plus 1 in the next bucket, and we are left with a scalar of minus 25. 25 is then smaller than 2 to the power C minus 1, so we only need to keep 2 to the power C minus 1 buckets for every window. This saves us half of these buckets for every window, so it will save us operations during the aggregation step or second step, and save us storage elements. The second optimization is the efficiently computable endomorphism that exploits a property of elliptic curves, that if you have an elliptic curve P, you can cheaply compute lambda times P, with lambda a scalar, a curve constant, by doing just one modular multiplication on the fly. How can we exploit this? Well, if we can somehow split up the scalar ki into 2 halves that are more or less half of the size, well, then we can go to different representation of the Pippinger algorithm, where instead of adding all of the points pi, we will now also be adding all of the points lambda times pi, so the endomorphism of these points, into the same windows, but because we have started from scalars that are half the length of the original scalar, we only need half of the windows anymore. So we only need to compute the aggregation step for half of the windows, and we only need to save the buckets, storage elements for half of the windows. The third optimization is quite similar in its gains. It makes use of pre-computation, and so what it will do is pre-compute values, 2 to the power C pi, 2 to the power 2 C pi, and instead of keeping a bucket set for every window, we will only keep one window, only one bucket set, and add the pre-computed points all into the same window. This way we only keep one window, only one aggregation step, but this costs us off-chip storage. Because we are pre-computing these values, we have to store them off the chip, and we need the necessary bandwidth requirements to get them onto the chip at runtime. These were the 3 optimizations. We combined them in our work, and the signed digit representation in the BGMW method or the pre-computation method are quite easy to combine because they don't interact that much. You just can reduce the size of the scalars by 1 bit by using SDR and then pre-compute all of the necessary pre-computations. The only downside here is all of this off-chip storage that we need. How many points do we need to pre-compute? Well, we have n points, ei with I going to up to n, and for every window we're pre-computing a value, so we have n times b over c different values that we need to store off-chip. By combining with the endomorphism property, we can cut this requirement by half. How do we do this? Well, we will first apply the endomorphism, so we are left with scalars that are only half the original length, and then we only need half of these pre-computations because we already are left with scalars that are only half the size. This comes once again at the cost of this one modular multiplication to compute the endomorphism on the fly, but this is quite cheap to implement. If we now look at what this means for the Pippenger algorithm, what does this mean for the number of elliptic curve point additions that we need to compute for one MSM? Well, then we look to the curve on the right here, where we have plotted the number of elliptic curve points you need for one modular multiplication in function of the window size. And then you can see that you want a window size optimally of around 1920 bits for the least number of elliptic curve point additions for one MSM. However, we cannot just choose any window size we want because we are restrained by the on-chip memory resources. That is what is plotted on the left. And there we can see that for our FPGA, if we want a realistic implementation, we cannot go for a larger window size than 12 bits. This means that we are left at this point on the graph. This is not optimal, so that is why we have implemented all of these optimizations and why we've combined them in our paper. So by doing this, instead of a window size of 12 bits, we can now go up to a window size of 17 bits with the same on-chip resources. And this means that instead of being left at this point, we can push it further and arrive at a more advantageous point. However, you can see we're still not done. We still want a larger window size if possible, but we are still constrained by this on-chip memory resources. That's why we went on to implement our iterative inter-MSM technique that allows you to reuse the same on-chip memory resources over many independent iterations that you can compute separately. How do we do this? Well, in our paper and in these slides, I have given you the example of 4 different iterations to save you 2 bits and reduce the number of on-chip memory resources that you need by a factor of 4. We want to end up with only 2 to the power c minus 3 different scalars that have to be added together, that we have to be accumulated in the first step. And so what we do is only select the scalars and the points that are corresponding to the iteration number and only handle those in this iteration. So in this way we can go to fewer buckets at the cost of memory bandwidth. Because what are we doing? Well, if you have the different iterations, every iteration will only be taking a fourth of all of these scalars that are corresponding with the iteration number. So in every iteration, we are discarding about 3/4 of the work. We need to make sure that we can keep our elliptic curve adder busy, that we can keep the pipeline filled. So we have to make sure that we are putting enough elliptic curve points and scalars onto the device so that we can keep the pipeline busy. There are some other issues here where if you go into the details, you will find that not all of the iterations have the exact number of operations that they do because there is a skew in the scalars. But if you read the paper, we have some extra details of how you can fix problems. We came from this figure. We wanted to go to a larger window size. Well, that is also what we achieved here. Instead of a window size of 17 bits, we can now go to a window size of 19 bits. You can also go to larger window sizes if your bandwidth allows you. And this allows us to push a bit further and go to fewer elliptic curve point additions for the same multiscalar multiplication. This brings us to some theoretical results. You can see that previous works on FPGA were stuck with window sizes of 12, maybe 13 bits, while we've implemented a window size with the same memory resources of 19 bits, and this makes it that instead of having around 300 million operations, we can do it in 200 million operations. There is this work that the previous talk also talked about, the LFG23 work. This is a CPU work and also was able to implement a window size of 19 bits. However, the software optimizations that they use even more pre-computation than the ones we suggested here, and this was just not feasible to implement onto the device. This was the first part of the talk about how we can reduce the number of elliptic curve points additions for one MSM as much as possible. Now we will go to some implementation details with Xander.
Hello. Before we go into the hardware implementation itself and give an overview, we first have to talk about bucket collisions. So whenever we have this simple design, we have an elliptic curve adder connected to a set of buckets, and then we have a queue where the points are stored and we fetch them over time. If you implement this type of structure in hardware, we often implement the elliptic curve adder fully pipelined because we want the highest throughput. This means that we can, every cycle we can start an elliptic curve addition, but it takes a number of cycles before the elliptic curve addition is finished. And this means is if you have a set of points that want to be added to certain buckets B, every cycle we can start a new addition. But at a certain point it can happen that the next addition that wants to start wants to be added to a bucket that is currently being processed in the pipeline. And this is a bucket collision. And to make sure that the result is still correct, what we have to do now is stall the pipeline up to the point that the bucket 2 is free again. And with a simple design, you can actually prove that you will lose around 10% of the total cycles just for pipeline stalls, which is quite significant. So that is why there has been a lot of literature on schedulers for this, and one of the better schedulers that you can find in literature is called the delayed scheduler. And they use two different kind of queues and a collision detector in between. And how it works is it will fetch every cycle from the first queue, and whenever a collision occurs, instead of waiting and pipelining, putting pipeline stalls, it will put that point in a second different queue, and such that the next cycle it can again fetch from the first queue. And so with this delayed scheduler design, actually the number of pipeline stalls so when the Q1 is finished, you switch then to Q2 and make Q2 empty, and if that collides, you put it in Q1. And so you can show that you only lose 0.2% of the total cycles, which is quite an improvement compared to the simple design. However, implementing this type of scheduler in hardware is quite a struggle because of the constant switching between Q2 and Q1, but most importantly, how large should you make Q2? Because you want it as large as possible because a lot of points can collide and you have to fill up the queue, but making it as large as possible means taking up a lot of resources. And you also don't want it too small because otherwise Q2 will fill up very quickly and then you're stuck again into the simple design. So that is why we took inspiration from the simple design and actually just added a second queue in parallel. So this means we have multiple queues, multiple points that arrive at the same time, have multiple queues in parallel, and then we have a collision detector that will fetch a point from one of the queues depending if there's a collision. So every cycle it will fetch from Q1, and then it will see that the next cycle it will fetch a point that is colliding, and instead of then fetching from Q1, it will directly fetch from second queue. Of course, it can happen, unfortunately, that both queues collide, and then we have to stall the pipeline, of course. And so with this simple design, we lose around 0.7% of the total cycles, which is a bit more than the delayed scheduler, but it's much more simple to implement in hardware. You can even extend the design to more queues, 3 queues for instance, and then you only lose 0.03% of the total cycles. So we took this scheduler and put it in our multiscalar multiplication algorithm, and then eventually implemented it on FPGA. And so this is a high-level overview of how our implementation looks. So we have a custom interface that is connected to memory, and we fetch both points and scalars. Since, as Thomas said, we use a window size of 19 bits, which means we have 14 windows in total, but because we are using the endomorphism property, we only need 7 points for each scalar. So the 7 points come in, a scalar comes in, and we first have to prepare the scalar. Scalar preparation means we have to split up the larger scalar in the 2 smaller scalars, such that we can use the endomorphism property, but then also use the signed digit representation to eventually get 14 subscalars, each with a negative flag indicating if you have to interpret it, the scalar as a negative or not. Then next, we have the point selection module, and here it's the point where we implemented our iterative MSM technique, because here we will look at the scalar and the current iteration, and if it's not in the current range of this iteration, we will throw away the point. Otherwise, it's selected and put into a new queue. Then we have 7 queues in parallel, because we have these 7 windows, 7 points. But our queue selection module, collision detector, actually has only 2 queues, so we have a queue selection in between, which just reduces the 7 queues to 2 queues. Then we have the collision detector. It will fetch a point depending if there is a collision, and then we first have to prepare the point. So point preparation actually just means we have to calculate the endomorphism of the point and calculate the negative of the point, and then select it if we need it. And since the endomorphism and the negative of the point act on a different coordinate, we can do these things in parallel. So afterwards, the point is added to the bucket. The whole bucket accumulation step is done. We also do the bucket aggregation, so the second step of the pip engine algorithm on hardware. And eventually, we have one result for each iteration, which is then sent back to via the memory interface to software to calculate the final result. So onto results, we have implemented this multiscalar multiplication onto an U55C FPGA from AMD. And we have 2 different setups. One is using 1 FPGA and running the 4 iterations sequentially. And the other one is using 4 FPGAs, each running 1 iteration in parallel. And we can run it at a frequency of 260 megahertz. And so with this, we can run MSMs of up to size 2 to the power 24 in 900 milliseconds for the 1 FPGA and in around 200 milliseconds for 4 FPGAs. This is a speed up, if we compare ourselves to other recent FPGA works, a speed up between 2.7 and 12.7 compared to related work. So in conclusion, in our paper, we combined the signed digit representation and the BGMW method, which are both known optimizations for the first time on FPGA, but we've also combined the endomorphism property with it to reduce the external memory and the memory bandwidth we actually need on our FPGA. And with this external memory bandwidth, we are able to trade memory bandwidth for reduced latency and memory, internal memory, using the iterative MSM technique. And with this technique, we were able to implement a window size of 19 bits, which is the largest FPGA implemented window size to date. If we, for example, then compare to a CPU paper that has the same window size, we have 6 times less off-chip memory compared to their approach using our iterative MSM technique. And so we all implemented this on a U55C FPGA and ran it at a frequency of 260 megahertz to eventually run MSMs up to size 2 to the power 24 in around 200 milliseconds. So thank you for listening, and happy to answer any questions.
Any question? Okay, let me ask one question. So you mentioned that this approach is applied to curves with endomorphism that can be efficiently computed. And did you try apply your approach on curves with endomorphism that is not efficiently computed? Do you still gain any performance improvement?
You mean with curves that don't have the efficient endomorphism?
With endomorphism that cannot be efficiently computed?
Yes. It's very interesting to look at it. We've not looked at it because we focused on one specific curve that has the endomorphism property. But if you don't use endomorphism or it's too expensive, you can still use all the other techniques, but you just need twice the memory bandwidth. And then to, I think, make it, you just need twice the memory bandwidth, I would say. So, but yeah, it depends on how efficient the endomorphism actually is. Mm-hmm. So yeah, we can look at it.
Okay. Any other question?
Thank you for the great presentation. I do have a question that it seems that your design is limited to the size of on-chip memories, and I can imagine that it is it's a problem for the IPJ implementations. And what if you port your implementation to ASIC platform? Do you have other options or solutions or other bottlenecks to your design? Thank you.
Thank you for the question. I think if we go to an ASIC design, we can just put as much memory as we want on the chip, but of course this will take area, so it will be a trade-off against how many elliptic curve adders we put on the chip. So then it would be a trade-off of how many compute units we want versus how much memory we want for the buckets. So I think it's a different trade-off. And as a first guess, I think it's still worth it to go to a second elliptic curve adder on the chip because you just have more parallelism available instead of pushing the window size as much. But thank you for the question.
Thank you. I have a follow-up question. So if we move the on-chip memory to the external memory, what might be the limitations there? Is the throughput or is the latency?
If we put the buckets off chip, we have the control of getting the correct bucket from the off-chip memory onto the chip at runtime. So it's not a sequential read of all of the just the elliptic curve points that are the inputs to the device anymore, but it's more of a random access. So the memory bandwidth, we can't use the fast speeds because now we have to select the correct ones. But it should be possible if you really have enough memory bandwidth, you can go to pretty much whatever window size you want, because off chip, these buckets are not a problem to store all of these results.
Thank you.
Thank you for the great presentation. I have a couple of questions. One is, in case I miss it, what's the kind of relative performance that you get in comparison with CPU's performance? And the other one is, what's the future work for this project?
So maybe first with CPU performance. So here we have the LFG work. Runs around 1.5 seconds compared to our 80 milliseconds, I would say. So it's quite a big improvement, especially if we use like the same parameters, same curves, and these things. And then for future work, I think we're looking at implementing and integrating this into a full ZK snark and trying to look at different building blocks that are also in these algorithms and also try to accelerate these so we have a full application. Because currently we only have the multiscalar multiplication running, and we want to also accelerate the other parts of the proofs.
Okay. For the CPU comparison, that, for example, includes SIMD implementation of vectorization like we saw in the previous presentation?
Previous presentation compared to the same work, to the same LFG, so I think they reported a 12x improvement, I'm not sure. We can take it offline and compare with the other authors, but if you take the parallelization over SIMD, you can gain over this work already.
Okay.
But, yeah. We would need to compare the numbers offline after the session to get you a full answer.
Yeah. Also, this work can be implemented on ASICs and get a much better performance too. Okay, thank you.
So if there's no other question, let's thank all the speakers for this session.